Trigonometry, a word first introduced in your geometry class. I know you were sleeping in that class, so in this video, we'll be going over almost all of trigonometry, from SOHCAHTOA all the way to Green's theorem. Wait, no, just SOHCAHTOA. Trigonometry is basically all rooted in this shape called a right triangle. Now, what is a right triangle? If you don't know the answer to that question, please click off this video and learn what that is. Other than the right angle, there are two other angles. Let's call one of them theta. Theta is just one of the many symbols we use from the Greek alphabet. It serves as an input argument for trigonometric functions like sine, cosine, and tangent. It relates angles to the ratios of side lengths in a right triangle. So what does that actually mean? It means sine, cosine, and tangent are just fancy ways of saying divide this side by that side. That's it. That's the whole secret. You can close the video now. Just kidding. Let's say this is our right triangle. We've got three sides: the hypotenuse, the opposite side, and the adjacent side. The hypotenuse side being the side opposite of the right angle, the opposite side being the one opposite of theta, and the adjacent side being the one next to theta. And this is where SOHCAHTOA comes in. SO stands for sine equals opposite over hypotenuse, CA stands for cosine equals adjacent over hypotenuse, and TOA stands for tangent equals opposite over adjacent. Now, if we look at this very easy example, we can clearly tell that sine theta is 3 over 5, cosine theta is 4 over 5, and tan theta is 3 over 4. Okay, moving on. Actually, one more thing before I move on is secant, cosecant, and cotangent. These are basically just the reciprocals of sine, cosine, and tangent. Okay, this is future Tim here, and I'm very lazy right now and I don't want to do animations, so for a little bit of the video, I'm not going to be doing any animations. Okay, back to the video. Now, the next important thing to know are common types of triangles: the 30-60-90 triangle and the 45-90-45 triangle. These are triangles which have specific ratios, so we don't have to calculate the side length. Before I forget, there's actually one more thing I need to teach, and then I can move on to the unit circle. Also, why was that guy holding two fingers? I said one more thing.
You're not that guy, pal.
That one more thing is inverse trig. Instead of theta, the input is the ratio and the output is theta. Wow, this is much easier than coding and animating the animations I've been doing. Anyways, we are finally moving on to the devastating unit circle. It's actually not that hard. This picture is overcomplicating it. Here's the real picture. The unit circle is a circle on a plane that has the radius of 1. It's used to define sine, cosine, and tangent with the equation x squared plus y squared equals 1. There are also 360 degrees in a circle, or 2 pi radians, which you can convert by using pi over 180 or 180 over pi to convert from radians to degrees. Now, how is this related to anything I said before? If we drew a right triangle in this circle, we can understand how we define sine and cosine. Since the radius of the circle is 1, the hypotenuse is 1. If this angle is theta, then sine theta would be opposite over hypotenuse. The opposite side is just the y value of this point, so sine theta is just equal to the y value of this point. Cosine theta is adjacent over hypotenuse, and since adjacent is along the x-axis, it is just the x value of this point. Now that we know this, these are the sine, cosine, and tangent values for the common 30-60-90 triangles and the 45-90-45 triangles. If you don't understand why it's these, pause and try to do so using SOHCAHTOA. Now, if we put this in a graph and move the triangle into the second quadrant, cosine theta would change and be negative because it is in the negative x values. If we moved it to the third quadrant, then sine and cosine will be negative. If we moved it to the fourth quadrant, only sine would be negative. We haven't really talked about tangent, and tangent is quite simple. It's just sine over cosine, so whenever sine or cosine is negative, tangent is negative. If sine and cosine are both positive or negative, then tangent is positive. Here's a short little phrase to remember it. All means all trig functions are positive, students means sine is positive, take means tangent is positive, and calculus means cosine is positive. Now, my favorite part is the graphs of these functions. Here are the graphs of sine and cosine. Here is an animation showing the relationship between a unit circle and the graphs of these functions. Since tangent is sine over cosine, it works slightly differently because of the asymptotes. Okay, I'm not coding this because it seems too hard, but since sine equals 0 when theta is pi over 2 and 3 pi over 2, there are going to be asymptotes there in every multiple of that. From theta equals 0, as you slowly approach pi over 2, cosine gets progressively smaller and sine gets progressively larger towards 1, so tangent will increase without bound. Going the other way, if theta is negative and approaches negative pi over 2, then cosine gets smaller and sine approaches negative 1, so the graph will decrease without bound. There are certain properties of these sine and cosine graphs that you can change that changes the graph. First, amplitude and period are basically the height and width of the function. Here we have a cosine function, and as you can see, changing the amplitude does not change the period. The phase shift is just the horizontal displacement of the function. And finally, the midline shows the midline. What a bad definition. Almost done now. We have to go over some identities. Remember this equation? I hope you didn't forget. Well, since sine is the y value and cosine is the x value, we can substitute them into the equation and get our first identity, the Pythagorean identity. We can manipulate this equation to get more identities. Here are other identities just from dividing sine and cosine on both sides. Now for our last topic, we will be talking about law of sines and law of cosines. It's for trig with triangles that don't have right angles.
What?
In this triangle, sine A over A is equal to sine B over B, which is also equal to sine C over C. I'm too lazy to prove this, so if you want to see a proof, see the link in the description. Last but not least, the law of cosine helps find a specific angle or side length of a non-right triangle. Alright, that's it. Now go to bed and pass that test. I know it's 3 AM.